In control engineering, discrete time system is important. This video introduces characteristics of the discrete time system. In the textbook, page 164 to 117 is about discrete time system. In the matter of grader, week 04 is related to the discrete time system. In many cases, plant is expressed as a continuous time system. Controller is also obtained as a continuous time expression. However, it is required to consider discrete time controller for implementation. This slide shows a various expression of model. In case of transfer function, continuous time transfer function is given like this, and discrete time case, G is a parameter of the transfer function. In case of state equation, x dot equal ax plus bu is a continuous time case, but xk plus 1 is xk plus buk is the case of discrete time system. They are mutually convertible. We can obtain a discrete time model through system identification and then convert it into a continuous time model. This slide shows an entire control system, and plant is considered as a continuous time, and the controller discrete time expression is used. Geometric progression is similar to the discrete time system. In this slide, common ratio R is considered, and an plus 1 equal anr is given as a geometric progression. The solution can be given as follows. If R is in the range of -1 to 1, an converges to 0. In other case, an diverges. This slide shows the numerical simulation of an. We can find that in case R equals 0.98 and R equals minus 0.95 is converge, but if in the case R equal 1.02, in this case the singular is diverge. This is related to the state space model in discrete time setting. xk plus 1 equal axk, and the solution can be given like this. If A is in the range of -1 to 1, the system is stable. In case that the system has disturbance, the signal can be given like this. We can find that the disturbance elimination performance depends on the value of A. This is the first order state space model. xk plus 1 equal axk plus buk, and in this case A equal 1.1 and B equal 1. This is the case of unstable system. When we select uk equal 0, in this case the output is diverge, and also uk equal 1, in this case the output diverges to infinity or minus infinity. When we select feedback controller uk equal minus 0.2 xk, in this case the entire system becomes stable. This fact is related to the case of continuous time system. This is the three cases of controller, and by using each controller, each system is converged and they are stable. However, the performance depends on each controller. This is a case of third-order system, and ABC is given as a matrix and vectors for state space model. In this case, by using U equal 1 is a step signal, then we obtain the output like this. Discrete time system state space model is given like this. K is time step and X is state, U is input, Y is the output. N is order of system and A is N times N matrix. In case SO system, V is column vector and C is the row vector. Y equals CX is the output. For discrete time system, the necessary and sufficient condition for asymptotically stability is that all eigenvalues are within the unit cycle. As an example, second order system is considered. Case 1 and case 2 is stable and case 3 and case 4 are unstable because the all eigenvalues are in unit cycle or not in unit cycle. For case 1 and case 2, each signals are converged to 0, but in case 3 and case 4, the output is diverge because the system is unstable. In this slide, the stability analysis using Lyapunov function is explained. Discrete time system is given like this and analyze stability without calculating state trajectory of the system. Quadratic form is given as a function is similar to continuous time system, and differentiate of Lyapunov function is given by vk plus 1 minus vk and can be given as x transpose a transpose pa minus p x, and we can consider Lyapunov equation like this. A is a given system and P, Q are the matrices. When we can select positive definite matrix P and Q, and the Lyapunov equation is satisfied, then for any x, V is larger than 0 and delta V is smaller than 0 holds. So V goes to 0 for each time. This is a case of Lyapunov inequality. When the Lyapunov inequality is held and P is positive and Q is positive, then for any x, V is larger than 0 and delta V is smaller than 0 holds. So V goes to 0. If this statement satisfied, the system is stable. This is an example of scalar system. xk plus 1 equals 0.9 xk. In this case, the system is stable. When we select the Lyapunov function as px squared and p equals selected as 1, then the time variation of Lyapunov function is given like this and can be given as minus 0.19. In this case, when we select q equals 0.19, the Lyapunov equation is satisfied. In this case, Since Lyapunov function is given and Lyapunov equation is satisfied, the system can be regarded as stable. For case 1 and case 2, we can select Q and P that satisfy Lyapunov equation. But in case 3 and 4, there are not exist solutions. These figures show the time series of the function value v. We can find that each value v is reduced for time. The relationship between continuous time and discrete time system is presented. In case of continuous time system, x dot equal ax plus bu is obtained. On the other hand, in case of discrete time system, xk plus 1 equal axk plus buk is held. It is required to mutually convert it. Continuous time system to discrete time system. We consider the input is fixed during the constant sampling interval delta t. In addition, the output is observed at constant sampling interval delta t. In such framework, continuous time system and discrete time system are related. If delta t is sufficiently small, almost the same dynamics can be expressed by the discrete time system expression, like this. Solution by state space model is given by this equation, and the state after delta t is given by this form, where this part is matrix exponential function. When we select input ut is fixed in the range t to t plus delta t, then we can obtain the following expression. And we can find that this is a kind of discrete time system.